Okay, the first thing we're going to do is we're going to look at Kirchhoffs Laws. Now, in the handouts that we've given you, obviously there's some descriptions of Kirchhoff, but what I'd like to do is do a quick example. Here's an example of currents flowing into a point on the page. If we call this current I1 and this current I2 and this current I3, the way Kirchhoff would have described this is to say that all of the currents that flow into this node here would equal 0. And for that to happen, I1 would have to be a positive current, I2 would have to be a positive current because they flow into the node, and I3 flows out of the node, so that would be negative. So you would write that I1 plus I2 minus I3 would equal 0. Now obviously, if you were to rearrange this, it would probably seem a little bit more sensible to write I1 plus I2 equals I3. That's quite simple. So whenever you come across a circuit where the current can branch, you can use Kirchhoffs laws to write the current equation for that particular node. We normally abbreviate Kirchhoffs current law as just KCL. Okay, that's easy. Now the voltage law requires a little bit more thought, but here we have the cell of a battery. Now if we want, we can have more than one cell and make a battery like that. Usually we call this an EMF. So any kind of voltage source is called an EMF. It produces a voltage, but we don't tend to call it a voltage, although if you look at a lot of videos, they might say the supply voltage. What they should be saying is EMF. If we have a couple of resistors in the circuit, like that, and let's call that resistor 1, R1, and that resistor 2, then because you've got an EMF and you've got an enclosed circuit, so we've got a circuit here, then current will flow. So here we are, we have some current flowing around the circuit. Now Ohm's law says that V equals IR. I'm sure you all know that. And if we have a current passing through a resistance like we have here, there will be a volt drop created. And the volt drop, the arrowhead on the volt drop, will point in the opposite direction to the direction of current. And there's a good reason for that, because we're saying that if the current flows clockwise around this circuit, then the voltage at this point must be higher than the voltage at that point. And the arrowhead on the arrow will always go at the side which has the highest voltage. Just as with the EMF, look, the EMF, the output of this battery here is that voltage here is higher than that voltage there. So the arrowhead is pointing upwards because it's pushing the current clockwise. The volt drops will be anti-clockwise because the voltage here is higher than the voltage there. Similarly, as the current passes through R2, there will be another volt drop. The voltage at this point here is going to be higher than the voltage at this point here. So the arrowhead will oppose the current. And we call this one V1 for voltage drop 1, and this one V2 for voltage drop 2. So Kirchhoff's voltage law is simple. We write that the EMFs in the loop must be equal, or must oppose, the volt drops in the system, and the EMFs and volt drops, the sum of which will always be equal to 0. So again, we can rearrange this and say that E1 equals V1 plus V2. So in any closed loop, like we have here, the sum of the EMFs will equal the sum of the volt drops. and there may be more than one EMF. The EMFs may agree with the direction of flow, they may oppose each other. And we'll do some examples like this. We normally abbreviate this to Kirchhoffs voltage law. Okay.